Okay, we already learned before this about the basic principle of GC, basic component of GC, the injection method, okay, until split and splitless, when to use and when not to use. So let's look into the next part of the GC components, which the column. Okay, the column is the heart of the separation system and is responsible for the resolution and efficiency of the chromatogram. So we have two keywords over here, efficiency and resolution. Okay, so without the column we cannot separate the components. Okay, so we need the column to separate the components. Okay, or we need to separate our analytes. So the column is the one who responsible for resolution, the peak is separated or not. Okay, or how good it is it good efficiency or low efficiency. Okay, so it depends on the type of column that we choose. Okay, so generally column can be divided into two, which is packed and capillary column. Okay, packed column is mean that in the center of the column you pack with the solid particle. Okay, so million of micron of solid particle. In the capillary column, it means that in the middle is empty, nothing here. Okay, nothing in the middle. So it's either you have the solid support at the wall of the column, or you coated with the liquid, or only liquid coated on the wall. So if we look over here, okay, if we look over here, sorry, I hate this. Wait. Okay, if you look over here, we have four. We have porous layer open tubular column. We have wall coated open tubular column, and we have solid coated open tubular column, and fused silica open tubular column. Okay, if we compare, okay, packed column is the first one invented, and then PLOT, porous layer open tubular column. Then somebody invented the wall coated open tubular column, and then somebody invented the solid coated open tubular column. Before, okay, the last one, fused silica open tubular column was invented. Okay. Okay, we will look into the illustration of the column later on. Okay, in the next slide. Okay, right now here is the comparison figure of the capillary and packed column. Okay, capillary, if you look over here, is very small and very thin compared to the packed column. Okay, because in the packed column we need to pack the station face, so the diameter of the packed column is much more larger compared to the capillary column. Okay, but because of the capillary column, the packed column have a lot of disadvantages. That's why the researchers or the other inventor invented the capillary column. Okay. Okay, if you look over here, okay, the packed column, okay, usually the length about 5 meter to 50 meter. The capillary column, it can reach from 30 meter to 100 meters. So if we look by that alone, okay, as I said before this, if we imagine ourselves race in the competition of 100 meter, for example, okay, maybe in 10 meter, my distance and you, when we are running together, is not that different. But the larger we run, the larger the space that we compete. So maybe you run more faster than me, so you run more. The better the distance between us. Okay, for example, okay, here at 10 meter, here at 30 meter. Okay, so maybe at 10 meter, the distance between you, here is you, here is me. Okay, so the distance between us maybe just 1 meter, okay, apart. Maybe after at the 30 meter, so you reach first here, okay, then I left here about maybe 5 meter. So the longer the column, the better it is for the separation, the higher the resolution. Okay, that's why capillary column is best for that compared to the packed column. Okay, that's why the capillary column was invented. Okay, has been invented for the better separation. Okay, so if you look over here, okay, remember in the question we can ask you guys to illustrate. Okay, please illustrate the capillary and packed column, or maybe please illustrate wall coated open tubular column. Please illustrate porous layer open tubular column, and please illustrate solid coated open tubular column. Or we can ask you guys please illustrate the fused silica open tubular column. Okay, let's go one by one here. Okay. If by history, packed column just wall of steel, okay, and then we have so many solid particle micron. Right now, I just draw as large. In your examination, if ask you guys to draw the packed column, you don't need to make the dot aspect as this. It's very hard for you. Just make it a circle a lot larger also. Okay, so it will take less time. Then if we compare it with the capillary column, okay, we just say here is the wall and then the inner is empty. Okay, so open tubular, or we can call as the open tubular. Open tubular is mean that in the middle is empty. Okay, okay, so after the packed column, okay, the next column invented is the porous layer open tubular column. Okay, because the efficiency of separation of the packed column is not that good. Okay, a lot of problem, the what we call the bleeding problem. Later on, we will look about that later on. So they invented the porous layer open tubular column. Okay, but the problem here with the open tubular column, here is the open tubular column. It means if we compare, okay, if we look back here, okay, compare to the three others, okay, compare to three others, okay, here we have the liquid involved. Okay, for the PLOT we don't have liquid, no liquid for the porous layer open tubular column. Okay, in GC, okay, before we going further, okay, in GC we can divide into GLC and GSC, gas solid chromatography and gas liquid chromatography. Okay, for gas solid chromatography is packed column, okay, and also the porous layer open tubular column. For the gas liquid chromatography, it can be packed also, it can be wall coated, solid coated, and fused silica open tubular column. Okay, remember, gas liquid chromatography, it can be G3 and also packed column. It means that, okay, in the packed column, okay, this solid particle is coated with the stationary phase, also can. For the GSC, it can be packed column and also PLOT only, porous layer open tubular column. Okay, so after the packed column invented, it can be either GLC, gas liquid chromatography, or GSC, gas solid chromatography, because they feel that, okay, the efficiency of the separation is not that good. Okay, the efficiency is not that good. A lot of column bleeding, so they invent the porous layer open tubular column. So remember, porous layer open tubular column, there is no coated inside of the acronym, so there is no coating, there is no liquid involved. Okay, just remember like that. If we have C inside of the acronym, it means that it has some coating, so it has the liquid phase. Okay, so after porous layer open tubular column, yet the, of course, after the efficiency increase, but the separation is not that good. The separation is not that good. It's still not great. So they invent the wall coated open tubular column. Wall coated open tubular column. Okay, for the porous layer, okay, the other problem with the porous layer, before I go further, the other problem, okay, of course, the one of the problem is the, of course, as I mentioned, it can provide a better efficiency, but still not that great. Okay, the problem is with the main problem with the porous layer open tubular column, it's suitable only for volatile compound, and also the one that has low molecular weight. Okay, so the PLOT is only suitable for volatile and low molecular weight. So how about the other one, which has a higher molecular weight, has the compound that is not that volatile? So they need to invent something. Okay, how they can introduce more interaction to the analyte. So after that, where they actually Okay, they actually invent the wall coated open tubular column. Okay, so in the wall coated open tubular column, there is no solid involved, so it's only wall and also liquid stationary phase. So when they invent it, so more interaction can be occur to the one that is less volatile, okay, and also high molecular weight. Okay, so there is where actually wall coated open tubular column is invented. Okay, but the problem is, okay, the problem is that uh, wall coated in the early day, they can only apply a very thin of the layer of the coated. So when we have the low layer of the coated, it means that it cannot hold the same the amount of the sample that can be hold is only small. Okay, the amount of the sample that can only retain by this liquid is small. Okay, of course it's greater compared to the PLOT, but it's small compared. It's still small. It's not that huge. So when so at high concentration amount of sample, okay, this will be a problem. So how they can increase the capacity? How they can increase the capacity is they invented, okay, they invented the solid coated open tubular column. So they invented the solid coated open tubular column. So they have the liquid, okay, that attached to the solid support, so they can increase the amount of the liquid coated onto the surface, so they can increase the capacity, so more amount of the sample can interact with the stationary phase better. Okay, there is where there is when solid coated was invented. But nowadays they have the technologies where they can increase the thickness of the coating without the additional of the what we call solid support. Okay, like here, without the additional of the solid support, they can already increase the thickness of the wall coated. Okay, before we going further later on, okay, just to make you understand, because I have mentioned about the fused silica open tubular column right here, right? So just directly want to mention to you, okay, why we need the fused silica. Fused silica is mean that we have open tubular column over here, we have the stationary phase over here, and then we have the fused silica over here, and then we have the wall lah. So it means that we have, here is the wall, here is the fused silica, okay, and here is the stationary phase, the liquid stationary phase, and also we have the open tubular over there. Okay, so before fused silica was invented, before fused silica open tubular column was invented, okay, most of the column were made of steel. Okay, were made of steel. So made of steel. So the problem with steel, they will react with acid, amines, and sort of other compound. Okay, steel is very sturdy. It's very sturdy. So but they will react with the acid and amine and whatsoever. So they will react. Okay, the column will have a lot of reactivity. Okay, then after that they invent, okay, throughout these years, after they using the steel have a lot of reactivity, we have a lot of reactivity with the wall of the column. Okay, it will damage the stationary phase, it will damage the stationary phase. So the column is not robust, the column is fragile. Okay, they tend to react. So they come up with replace the steel. Okay, they replace the steel, okay, with glass. Okay, they replace the steel with glass. Okay, but the problem with glass, the glass, yes, of course, after they replace the glass, they are able to solve the problem of the reactivity of the column. Okay, but the problem with glass, okay, glass is fragile. Glass is fragile. So they invented the fused silica open tubular column, where in the fused silica, here is the wall. Okay, in the silica, the silica is not only silica, it's the fused silica. Okay, if the glass is only silica, right? But the term fused silica is mean that they combine some of the elementary, the inert earth element. Okay, they fuse with silica to strengthen the column. So they make the column much more stronger, much more robust. So as I described earlier, from the porous layer of tubular column, from the packed column where the efficiency is not great, they invent the open tubular column. But the first stage of the open tubular column, okay, they try to invent better efficiency, but suddenly at the end they start, okay, the column is react to the acid, so some problem. So they invent the glass column. When they invent glass wall column, the problem is that it's fragile. So as compared to the normal silica glass column, so they infuse the silica. Okay, they infuse the silica with some of the element. Okay, so they increase the strength of the column. So that's why it come up with the fused silica open tubular column. I hope that I already described very well about the column. Okay, let's look into pack vs capillary column. Okay, let's look into the pack column first. Advantages of the pack column: it can provide a greater capacity, can handle large mass of injection, large volume of injection without damaging the column. Okay, and also the pack column is lower cost compared to the capillary column. Capillary column, the production of the column is much more tedious. Okay, much more tedious. Okay, because the diameter is very small, right? Compared to the pack column, we can just pack the stencil piece. Okay, but in the pack column, it has a lot of disadvantages. Okay, first, lower theoretical plate number is mean that the efficiency is not that great. Efficiency is not that great. It means that pack epic you will get is broadened. It's not sharp. Okay, that is the problem with the pack column. Okay, then it require large amount of carrier gas. Of course, if we compare to the capillary column is very small, right? The pack column is much more huge. So you need the higher number of higher volume of the mobile phase or carrier gas to bring your analytes until it reach the detector. Okay, until it reach detector. So it will, of course, even though the pack column is not that costly, okay, but the carrier gas is very costly as well. Okay, so that's why they try to improve the idea how actually they can what we call reduce the problem to use a low amount of gas. So that's why they invented the capillary column, okay, which is use less lot of the carrier gas. Okay, then the pack column, the other disadvantage of the pack column is the large amount of bleed, large amount of column bleed. What is mean by large amount of column bleed? Okay, column bleed happen. Okay, column bleed happen when the pack column, okay, especially, okay, if in the pack column, okay, for example, if the pack column, okay, usually it must supposed to be very close. The packing material must be very close to each other. The problem is when the column is damaged, maybe due to not properly well maintain the temperature, or some of the solvent used damaging the packing beads or packing material, so they will create, for example, the empty spaces. Okay, they will create empty spaces. Okay, when this happen, okay, they will create a lot of instability. So your peak will have a lot of noise. The base chromatogram, you have a lot of noise. That will be a problem for the large amount of bleed. Compared to the capillary column, okay, you only have the stationary phase on the side. Okay, so if anything happen, it only happen on the side. So the characteristic of the bleed, okay, of the capillary column is less compared to the pack column. Okay, so that's why later on when we look at the capillary column, it is more robust compared to the pack column. Even though pack column is quite big, but it's not that robust. So we can say that kalau kata badan besar, badan sador ni tak semestinya hati kering. Kadang-kadang badan kecil, badan kurus tu lain, hati kering. Okay, that is kind of the analogy that I can give to you. Okay, so the packed column cannot handle fast heating program. It may damage the column, so the bleed will happen. That is the problem. Okay, before I'm going further to the capillary column, I would like to describe a little bit about the bleed effect. Okay, the bleed effect, there are two appearance of bleed effect. Okay, the first thing is, okay, if we compare, if we how I can do this. Okay, let's look over here only. Okay, the first thing is, okay, if we compare to the, let's say, characteristic of the bleed. Okay, say bleed and non-bleed. Okay, the characteristic of the baseline. The baseline is mean that the baseline at the chromatogram. It mean that the lower baseline lah, the lower baseline. Okay, that is the baseline. Okay, for the bleed column, the column that has the bleed characteristic, the problem is that they have a lot of noise. Okay, for example, okay, they have a lot of noise. Okay, the non-bleed column, okay, the line should be much more smooth compared to the column that is actually bleeding. Okay, the second characteristic, if you look over here, okay, for the low bleed, the what we call the baseline is stable. The baseline is stable. It means we get a very straight line. Okay, but at high bleed effect of the column, are at the certain temperature, because of the pressure much more higher. Okay, the effect of the pressure is much more higher, so it can create the higher baseline of the chromatogram. Okay, so what is the effect? Okay, the problem is with the quantification. Okay, the bleed is not good for the quantitative analysis. Why? Okay, for example, you have the clean baseline. Okay, if we compare the one that has a jaggery, sorry, maybe my drawing is not that good. Okay, so it will disturb your quantification. Okay, and for example here, if for example at the low bleed characteristic, in the second characteristic is, for example, at the higher retention time, you get a very huge bleed. Okay, if the column is no bleed. But if the column have bleed, okay, then chromatogram suddenly increase the baseline, and then you only see very small peak. So if we look over here, this one is better for quantification. Okay, there is the bleed effects that could disturb your analysis. Oh, sorry. Let's look, okay, on the capillary column advantages and disadvantages. Okay, capillary column can give you best resolution. Okay, this is my mistake actually. Best efficiency and also resolution, both. Okay, it can provide a better separation, and also the peak will be sharper compared to the packed column. Capillary column also more robust, less tend to the what we call bleed characteristic. Okay, better sensitivity and efficiency is actually reflect the same thing about this thing, this one and also this one. Okay, low bleed characteristic, okay, because it's more robust, require less carrier gas. Okay, so it can save your money, but the disadvantage is quite expensive. It's quite expensive. Okay, robust. Okay, in the term of robustness, of course, the capillary column is much more robust. So we don't have the problem with the column bleed. But we need to have in our mind, even though it's robust in terms of when we try to adjust the temperature, in terms of fragility. Okay, the toughness of the column. Okay, is the packed column is much more tough compared to the capillary column. Capillary column is much more fragile. Okay. Okay, here is the description. of the type of column, we have the based on the capillary column, not the packed column. Okay, we have the wall coated, solid coated, porous layer open tubular column, fused silica open tubular column. Basically, this is supposedly to be the first one. The second one is the wall coated. The third one is the solid coated, and then the last one is the fused silica open tubular column. Okay, never mind about that. Okay, wall coated open tubular column, a capillary column, tubes coated with thin layer of the liquid surface. So we have the wall that actually coated with the liquid. So you can say here is the liquid. Okay, support coated open tubular column have inner surface lined with thin film of a solid support material. So we have the solid over here. Okay, that actually coated with the liquid. Okay, porous layer open tubular column. Okay, of course you only have the this particle. Okay, without the solid coated. Okay. Fused silica open tubular consists of polyamide coating. Fused silica and this tertiary phase which strength provided polyamide coating give more physical strength. Okay, give more physical strength. Okay. Alright, let's look into the wall coated, solid coated, and porous layer of the tubular column. Okay, here is the what we call the cross section. I think we already described this thing here. So here is again the repeatance of those illustration. Okay, for the capillary, it can range from 10 meter to 100 meter. Okay, 30 meter is the normal range actually for the capillary column. Okay, so it can reach up to 100 meter length. Okay, if you look over here, the inner diameter is less than 0.1 mm. Less than 0.1 mm. So I also cannot imagine how they produce this column. I cannot imagine by myself because I don't have that kind of experience produce this column. Okay, alright. Okay, in the fused silica particular column, here is the fused silica tube, and the wall is made of by the polyamide coating. So it's increased the flexibility of the column. Okay. Fused silica capillaries are drawn from specially purified silica which contain minimal amount of metal oxide. Fused silica capillaries are given added strength by outside protective polyamide coating. Okay, so they actually fuse silica, and then the outer of the fused silica they have the polyamide coating. Okay, so it increase the physical strength, reduce the reactivity, and also it's give the flexibility to the column. So your column less fragile, also less reactivity. So these the advantages of the fused silica column. So let's say the question asks, okay, please among of the 4 types of the GC column, capillary columns, describe which is the best column. Okay, describe the best column and state the advantages. So you need to be able to select which kind of the column is the best. Of course, for the time being, fused silica open tubular column is the best one so far. Okay, but of course the price is quite expensive. Okay, let's continue to the next part, which is let's look into the effect of the column length. Okay, as the column length increase, it can give you a better efficiency and resolution. Okay, it can give you a better efficiency and resolution. It means that more peaks of analyte can be separated. For example, in 50 meters, you are not able to separate 5 analytes, for example. Maybe 60 meters, it can separate all the analytes. So it can provide a better efficiency and also resolution. Okay, but the problem with the effect of the column length, of course, the retention times are longer and assay are slower. Assays mean that the process is slower since a lot of time is taken to what we call elute all the analytes. Okay, but the best thing is we can spread all the analytes. So if you are asking me if I prefer the time is faster or I can separate everything, I will say that I prefer that if I can separate all the analytes. Okay, so better go for the sorry about that. Better go for the column that is quite lengthy, so it can give you a better separation. Okay, the next one is the effect of the column IT, or we can call it the internal diameter. Narrower columns give increased efficiency, so don't use the column that has large internal diameter. If you have option for the column that has low internal diameter, so you go for it. Okay, column that has less internal diameter, they will provide a better efficiency and resolution. Okay, if you look over here, for example, here is 0.1 millimeter and here is 0.25 millimeter. If you look over here, the separation of this peak is much more better at R equal to 4.0. Okay, however, for this one, if we look over here, it's still separated, it's more than 1.5, but yeah, it's close to 1.5. So the one with the smaller internal diameter will provide a better separation or better efficiency or better resolution. If you look over here, it say can narrower columns give increased efficiency, reduce detection time, but reduce sample loadability and more injection problem. Okay, what it means by this? Okay, sample loadability, you cannot inject at high volume. Okay, you cannot inject at high concentration, because when the column internal diameter is lower, okay, is shorter, what happens is the thickness of the coating also is not that great, it's not that big, so you cannot inject a lot of sample. Okay, so when you have some if you perform wrongly, or you not maintaining the right procedure to care of the column, they will produce the injection problem later on. For example, if you keep injecting at high loadability, you will damage the coating of the column, since the coating of the internal diameter that is lower is much more thinner. So when you force higher volume of sample, it will damage the coating, and of course it will somehow affecting the injection problem. For example, later on we will learn about the I think you learn about what we call peak tailing, okay, peak splitting. Okay, that is the kind of the injection problem can be faced during the injection. Okay, the next one is the effect of coating thickness. Greater film thickness give increased detection time and increased loadability, but reduce efficiency. Okay, if you look over here, okay, to have a very great separation, okay, we need to use the what we call the thicker coating, the thicker coating. Okay, if we compare between these three, 1.0 micrometer of coating, it can provide a better separation. Okay, but here it mentioned that but reduce the efficiency. Efficiency is mean that if you look over here, the peak is broadened. Okay, again I would like to remind, if we want to compare the efficiency, okay, we look at the peak characteristic. If the peak is sharper, it means that the efficiency is higher. If the peak is broader, it means that the efficiency is not that good. Okay, that's why but again, if I would like to choose, okay, between separating and also efficiency, I will choose this separating come first, because we want everything to be separated. Later on we can try to adjust, okay, the parameters such as the flow rate, such as the temperature programming, so we can increase back the efficiency or the sharp to sharp the peak. Later on we can do that. Okay, but first of all, the main idea is to separate our compound. That is the idea of the chromatography actually. Alright, for the GC column, okay, let's look into the type of stationary phase. Basically, we can divide it into two non-polar columns and polar columns. It's different compared to the HPLC. We didn't call the GC as the reverse phase or normal phase, but we just call GC as gas chromatography. Okay. How we choose the column depends on our analytes. Okay. For example, for the non-polar columns, okay, it's suitable for separating non-polar analytes because non-polar will react with non-polar. If we use the polar column with the non-polar column, what happen? It will not be retained by the non-polar column, so it will not be separated. So for example, we want to separate the non-polar analytes, so it needs to be interacted with our column. So what kind of the column to interact with the non-polar analytes? So we use the non-polar column. So the non-polar column separation according to analyte volatility and also the polarity as well. So maybe add before this, based on analyte non-polarity. Okay. Retention increase with boiling point. Okay. Retention increase with chain length. Okay. What is mean by this? It's the same thing actually. Okay. For example, you have compound with 2 carbon and compound with 6 carbon. Okay, 6 carbon chain length. The higher the chain, okay, the more non-polar it is. Okay, so it will react with the non-polar columns more, the stationary phase more, so it will retain a lot longer compared to this one. Okay. So of course, when we increase the chain of the carbon, what happen is the boiling point also increase. So the retention time, okay, will be much more lower lah, much more longer. Okay. For the polar column, separation also based on the volatility, okay, and also to polarity. I forgot to add about here also, but here based on the polarity and above here based on the non-polarity. Okay. Polar analytes more highly retained compared to non-polar analyte. Interaction by H bonding or dipose interaction. So, for example, if you want to separate polar analytes. For example, you want to analyze type of alcohol available in the beverage. Okay, so you have the kind of standards. Okay, the standard is, for example, methanol, ethanol, propanol, butanol. You don't really know what kind of alcohol appear in the beverage. Okay, so in your opinion, which column is best for separating of that polar analyte? Because we know alcohol is polar. So if you use non-polar column, what happen is the non-polar column will not interacted with your analyte. So you use the polar column to make them separate. Okay. Order of elution can change between type of if analytes in a mixture. Type of analyte in the mixture. Okay, order of elution can change between types. Order of elution can change between types if analytes in a mixture have different functional. Okay, I think between type of the column. Okay, between of type of the column. If mixture have different functional group. Okay, it depends on the functional group. Okay, for example, if you just carbon 6 and carbon 2, okay, but if suddenly carbon 2 have the OH, suddenly it become polar. So it will change, for example, the elution order, for example. Okay, here is the effect of stationary phase. Okay, if you look over here, we have 4 kind of analytes. We have p-xylene, m-xylene, decane, and undecane. So basically, we have the mix of non-polar and polar analytes. So we have the NP. Here is the NP also. Here is non-polar as well. Here is little bit polar. If we sort by the polarity, okay, non-polar to the polar. Okay, if we observe over here, the most non-polar is number 4, the undecane. then is followed by number 3, and then is followed by number 2, okay, and then by number 1. Number 1 is the most polar. Okay, but again, okay, if we look over here, it's kind of a little bit special actually. Okay, if you look over here, let's say if we use the column that is non-polar. Okay, so number 4 and number 3 should eluted later because they are the most non-polar. So number 4 is the last one to be eluted. If we observe over here, right, as is the non-polar. Okay, maybe here is the column is not that big, it's not that lengthy, it's not that long. Okay, so number 1 and number 2 is not that separated. It's not separated at all. Okay, number 1 and number 2, because if you look over here, they have the same carbon number. But the differences is based on their structure. So compared to here, the compound, this one, sorry, I think I made a mistake over here. Let me, not 4321, 4321. Here is M. Betul ya? Here is polar, is polar. Here is M, here is para. Okay, so para is nombor 1. Okay, so para is not non-polar, so sorry, it should be like this. Okay, it should be like this. 4312. Number 1 is non-polar compared to number 2. Okay, sorry. 4312. If we change the column to the polar, so because we have the problem with this to spread these two compound. Okay, because we have the problem to spread these two compound, we cannot use the non-polar because it will not react with the non-polar. So what we can do, we change by using the polar column. Okay, at the polar column, since decane and undecane is quiet non-polar, it's not quiet, it's actually non-polar at all. So if you look over here, they will separate based on the volatility. So the shorter the chain, they will have the lower boiling point. Okay, again, the shorter the chain, they will have the lower boiling point. So they will eluted earlier because they will not react with the polar compound, right? Polar column. So if the non-polar will not react with the polar, so they will separate based on the volatility. The one that is more volatile, they will eluted earlier. So number 3 will eluted earlier. Okay, since it has a shorter carbon chain compared to number 4, so it will eluted earlier. Okay, later on, we see number 1 and number 2. Number 1 is para, number 2 is meta. Okay, if you look over here, the boiling point of them should be more or less like it's about the same. Okay, because of the structure is not that different compared to just the position of the methyl. So based on the polarity, since metaxylene, okay, the M xylene is little bit polar, so it will retain little bit longer compared to the P xylene or para-xylene. Okay, if we look over here, number 1 para-xylene, since it's a little bit non-polar, it's non-polar compared to the metaxylene, so it will eluted earlier than the metaxylene, which is retained. Okay, maybe the column here is not that long. Maybe we need to increase the length of the column so we can improve the separation better over here. Okay, here is other example of the column, the application of polar and non-polar column. Okay, for example here, above here the column is non-polar. Okay, the column here is non-polar, and below here the column is polar. Okay, sorry. Okay, but sometimes, if you look over here, the problem is when we use the column which is too non-polar. If the column is terlampau non-polar pun tak boleh juga. So kena pilih in between lah. Kena pilih in between. Okay. But sometimes we need to look actually what actually we want to improve. For example, kalau kata kita nak separate, we choose the non-polar column. Tapi kalau kata kita nak improve the retention time, we can use the polar column. But again, dalam kepala kena fikir apa-apa pun kita punya analytes kena separate. Kalau tak separate, tak guna pun kalau kita guna this column. Okay. Macam ni kita nak analysis hydrocarbons which is non-polar from C8, C10, C12, C4, C16, C18, 20, 22. If we look over here, okay, the column, okay, is non-polar and we can separate everything very well. Okay, in the non-polar column, in the polar column, okay, what happen is our non-polar analytes will not react with the column, so they will separate based on the volatility, based on the boiling point. If you look over here, we have reduced the retention time. We have reduced the retention time very well. Okay, but the problem is if you look at the C8, so it appears with the solvent peak. So this is our problem. Okay, basically actually in GC, you can use either column. Okay, you can use either column. For example, if you look over here, can we use the polar column? Yes, we can. But how to improve the C8 situation? Okay, you can adjust the temperature programming. You can adjust the temperature programming. Later on, I will discuss about that temperature programming. Okay, if we look over here, okay, the peak is tailing. Tailing is like this. Okay, okay, it means that it's not really suitable to be used. Okay, because it's react a lot with the column. Okay, it's react a lot with the column. So what can we use? Okay, there is several solutions. Okay, the first, okay, peak tailing usually appear because of we inject too much volume of sample, so we can reduce the volume of the sample. Okay, we can reduce the volume. Okay, reduce the volume. And the second one, we can perform the temperature programming. We can perform the temperature programming to improve the retention time. Okay, instead of 2 degree per minute, maybe we can increase to 2 degree per minute increase. Okay, so if for example, if you compare here, okay, it used 2 degrees C per minute. To improve the retention time, maybe we can increase to 3 degrees Celsius per minute to improve the retention time. Or if you want to improve the chromatogram even more, as we can also suggest to use semi-polar column, which is we can still separate and also we can improve the retention time as well. It's not non-polar, it's not either too polar, it's not too non-polar, it's not too polar. So we can have a lot of variables we can adjust, okay, during the analysis. Okay, usually for examination, we just only decide, okay, between the non-polar and polar, which one you prefer for separating the non-polar hydrocarbons, that kind of example. So maybe you can suggest, okay, to separating non-polar analytes, we better choose the non-polar analytes. Okay, let's say based on you choose the non-polar analytes, so how you can improve? Okay, let's say you choose non-polar columns. Maybe the question further asks you how you can improve the retention time. Okay, maybe you can say increase the temperature programming, or maybe change to the non-polar semi-polar column. Okay, or maybe you can say that what else, increase the flow rate. Okay, that is the kind of thing that you can play around. Okay, you can play around. Okay, so we have done about the column. Okay, first of all, we done with the injector, gas carrier, and then we done with the column. Now let's proceed with the oven. Okay, oven is where you can control or uniform the column temperature, okay, when is required. Okay, column temperature is slightly above the boiling point of the sample. results in elution time of 2 to 30 minutes. Okay. Minimal temperature give good resolution but will increase elution time. Okay. Okay. Let's say, so everything here is the information is required. Okay, you need to understand. Okay, it's not that I would like you guys to memorize. Okay, memorize is the thing that I always fail. Okay, but we need to understand. Okay, in the oven is the one we can control or we can uniform the temperature of the column. For example, we want to set at certain degree Celsius. We want to maintain at certain degree Celsius, or we want it to increase, okay, 5 degree per minute, okay, or maybe we want to increase 10 degree per minute. For example, from 20 minutes, okay, from 20 degree we want to increase to 300 degrees Celsius. Okay, we can either use maybe 2 degrees C or maybe 3 degrees C, or we can also set up 10 degrees C. Of course, if we compare over here, 2 degrees C, if we use 2 degrees C per minute, 2 degrees Celsius per minute, okay, it will take much more longer to reach 300 degrees Celsius. 10 degrees Celsius, if you choose this, okay, you will reach, okay, to 300 much more earlier. Okay, what is mean by this? I'm not really sure if you have learned in the instrumentation analysis whatsoever. Okay, but it's about the same. Okay, this means that every minute, okay, it will increase. Sorry, maybe I write it wrongly. Okay, I don't want you guys to get confused. Okay, for example, 2 degrees C per minute. Sorry, per min. Okay, 3 degrees C per min. Okay, 10 degrees C per min. It means that every minute, okay, if you look over here, it will increase by 2 degree. Okay, for example, in the minute 1, you will increase to 22. In minute 2, you will increase to 24. It will increase 2 degree per minute. For example, if 10 degrees C per minute, so, it will increase 10 degrees Celsius in a minute. Okay, within a minute. For example, in minute 1, okay, it will increase to 30 degrees Celsius. In minute 2, it will increase to 40 degrees Celsius. So you will reach the 300 faster here compared to here. Okay. Column temperature is slightly above the BP of the sample results. Okay. For example, your analyte, okay, your analyte is at 75 degrees Celsius. Okay. So whatever it is, the column temperature should not, okay, should not less than this. Must be at least 20 to 30 degree higher than this. Okay, higher than this. Okay, if not, for example, okay, why I need you to remind you guys about this, okay, I'm afraid you doing the mistake during the analysis. Okay, for example, your analyte is 75 degrees Celsius, but in the oven you just set up at 50 degrees Celsius. So what happen is, okay, after injection, it's enter the column, right? It's enter the column. Okay, so for the analyte to pass through the column or to flow through the column and reach the detector, it must be in the gas mode. When your oven is not more than your analyte boiling point, it's less than your analyte boiling point, what happen is that your analyte will condense back to the liquid. It will not get separated and it will not reach the detector. So what happen, it will stuck in the column and also damage your column. That's why the oven temperature must be more than your analyte. Okay. So the optimum retention time of the analyte is 2 to 30 minutes. Okay, if your analyte is not that much, maybe 1 or 2, maybe you can just run within 5 minutes or 10 minutes. If your analyte is up to 10 or 20, so it's okay for you guys to reach 30 to 60 minutes. Depends on the number of the analyte. Okay, sorry. Minimal temperatures give good resolution but will increase elution time. If we use 2 degrees C per minute, okay, it will raise the temperature slowly, so it will increase the elution time. It will take a longer time to finish the assay or finish the procedure. Okay, but if you use too fast, the problem is, some of your analytes might not be separated. Okay, so we need them to be optimum. Okay, the analytes to be able to separate, but not too long, because we don't want the analyte to be broadened. Okay, so we want to keep the condition optimum, so you can have a very good resolution, but at the same time the retention time is not that long. Okay, there are two separation modes, which is the isothermal and also the program temperature. Isothermal mean that fixed temperature during the separation program. For example, your analyte is 75 degrees Celsius, right? So you stay at 80 degrees Celsius from starting, from 0 minute until 30 minutes. Okay, that's all. Until 30, sorry, not 30C, 30 minutes. Okay, because your light is at 75 degree. So you maintain the same temperature from the beginning of the analysis until the end of the analysis. For the program temperature, it means that you setting the change. For example, at 0 to 5 minutes, 0 to 5, you want at 20 degrees Celsius. Okay. Then from 5 to 10, you want at 100 degree Celsius. Okay. So you change. When we change the temperature, it's not the same from the beginning until the end. It means that we program the temperature. So temperature is increased or continuous or in step as separation proceeds. Okay. Usually, isothermal is used for the simple mixtures. Okay, very simple, not a lot. It's not a complex. Your analyte is not that much, and also your matrix is not that complex. But if your analyte is not that simple, your matrix is complex, so usually we use the program temperature for better separation. Okay, especially for sample of wide boiling range. For example, okay, you have analyte A. Sorry. For example, you have analyte A, B, C. If the temperature is about 65, 70, 80, so we say that the analyte is not that complex. The temperature is not that different. So you can use isocratic. But suddenly you have 65, you have 100, and then you have 200. So you have a wide boiling range of the analytes. The boiling range of the analytes. There is when you need to use the program temperature. Okay. For simple samples, separation may be carried out under isothermal conditions. Of course, the temperature, I already described about that. For sample with wide range of volatility, to use temperature programming to enable volatile compound to be resolved at low temperature and elution of later less volatile compounds to be speeded up as the temperature increase. Profile included of series of time, initial isothermal period, pause at intermediate fixed temperature, different RAM rates, final isothermal periods, and automated cooling down of column to initial temperature at end of run, ready for the next cycle. Okay, what is mean by that? Okay, what is mean by that? I think I need to draw a bit. Okay, I need to draw a little bit. Okay, let's say you have compound A, B, C. Okay, here is 65, here 70, here is 80. So you can choose to run the oven at 90 degrees Celsius, for example, at isocratic. So later on, okay, it will get separated. Okay, why you cannot choose at 60 degree the oven temperature? Okay, the problem when you use at the 60 degree, there may not be a peak to appear because your boiling point of the light is much more higher. Okay, so for example, you choose at 75 degrees Celsius the oven. Okay, what happened? You will detect A and B. So C will not be eluted since the temperature of the C is much more higher. Okay, so it will start in the column. Okay, so it's very simple. Usually from target lights, we have we put the over temperature at isocratic at the temperature at least 30 degree higher. Okay. Okay, that is for isocratic. Okay, I should give you another thing, sorry. A, B, C. Okay, 60, 75, 80. Sorry, 60, 70, 80, let's say. Okay, so I give you these three conditions. Okay, the other thing you need to remind, okay, you cannot choose, for example, or suddenly you cannot choose 150 degrees Celsius. If you use like this, maybe your peak will appear like this as a single peak. Okay, you don't want the temperature is too different compared to this 2D analytes. Okay, if too different, okay, the temperature push your analytes together, there is no separation will occur. If you put the temperature is too high, so what happen? Your analyte will appear as a single peak. Your analyte will appear as a single peak. So you don't want that to happen. Okay. So let's say you have A, B, and C. Let's say you have A, B, and C, and then the temperature of the analyte is 30. A for the analyte A is 30, B is 100, and C is 250. Okay. Let's say for example at 30. Let's say for example at 30, you setting at 30, which analyte will appear? Okay, maybe only A. B and C will not appear. For example, you put analyte at 250. Okay. Or maybe I can give you, sorry, a better example. A, B, maybe here is 50. A, C is 100. D is 250. Okay, let's say. Okay, let's say I set up the oven temperature at 30. So only the one that appear is maybe A. B maybe appear. B maybe appear. But maybe. Okay. Okay. But C and D will not appear because the difference between the oven temperature and the boiling point of the light is too different, right? Let's say you want to solve the problem. You want to eliminate D. So you put at 280. Isocratic. So what happened? A and B will appear. Sorry. Maybe appear like this. So here is A and B. Here is C and D. Okay. So A and B will not be separated. C and D also will be separated. Or maybe what happen is, okay, A and B, and then after that C and D. So the possibility that okay, A and B is not separated, and also we have a lot of time here that is actually wasteful. Okay, kita buang masa kat sini, we waste our time over here, so we can improve that. Okay, so for example, that's why I cannot, that's why we need the temperature programming. For example, okay, instead of 250 or 30 degree alone, so what I will do is I will, for example, the first temperature I will begin at 50 degrees Celsius. Then I will increase 5 degrees C, okay, until maybe 10 degrees C per min until it reach 50. Until it reach 70, for example. Or maybe because the temperature A and B is not that different, so maybe I start with 50 degrees C, so I maintain for about 2 minutes. So 0, 2, 2. So to reach C and D, okay, so to reach C and D, so maybe I set about 10 degree C per minute. So from 50 to reach 100, 10 degrees C per minute, it will take 5 minutes, right? So at 7 minutes, so it will reach 100. Okay, it will reach 100 degree Celsius. It will reach 100 degrees Celsius. Then from 100 to 250, so maybe I don't hold at all, so I just increase more steep than that. Maybe here I change to 20 degrees C, or maybe I can change to 30 degrees C per minute. So from here, okay, 30 to 250, okay, it will take another 5 minutes. So at minute 12, I will reach 250. Or maybe we set up at until 280. So 280 will take about 30 minutes. Okay, 30 minutes. Okay, so 50, I hold for 2 minutes. Okay, so I adjust 10 degrees C per minute, so it will increase. Okay, then because of 100 to 150 is much more longer, so if we wait for 100 to reach 250, it will take about how many minutes? 10, 50. Okay, so we increase, instead of we wait another 50 minutes. Okay, if you look if we, instead of we wait for 50 minutes, we change to 30 degrees C per minute. It means that from 250 to from 100 to 250, it will take only about 5 minutes. So if we, for example, I set up to 280, because the rule of the oven, we need to set up 20 to 30 degree more than our last analyte. So I chose 280, so it will take about 6 minutes. So from here to here, it will take about 6 minutes. So by in 30 minutes, you will finish your analysis. So the chromatogram that we should get is like this, supposedly like this. So we should get A, B, C, D. So that's why we need the temperature programming. So here's the thing. Okay, here is the where we hold the temperature. Okay, here where is we RAM. Okay, how many degrees Celsius per minute. Okay, depends. And then maybe here we hold again. I'm not really sure, but it's the term. Yeah, the term is pulse, RAM rates, okay, cooling down. Okay, usually after we reach at the 240 and then we want to wait for the next cycle, we need to let it step down. For example, maybe 10 degrees C per minute until it reach 40 degree back. So we need to do that. If not, it will take a longer time later on. Okay, so here is the programmable temperature. We inject, we RAM, we hold, or we can call as pause. Okay, here is the final, and then we need to cool down until it reach the initial temperature. Then only we can inject again. You cannot inject the next sample at here. Okay, you cannot. You need to wait until it reach the initial temperature. Okay, here is the example of the isothermal vs temperature program. Okay, here we have the for example from C8 until C20. Based on the isothermal, maybe here he set at 200 degrees Celsius. So what happened? Some of the analytes is not separated. So maybe here is okay. Maybe the analyte of C8. Maybe just C8, C10, C12, C14, C16, C18, C20. So maybe I just put 70, 80, 90, the boiling point. I just put 90, 100, 110, 130, 150. I just put. Okay, maybe here he just run at isothermal at 115 or 120. Okay, so what happened? Okay, C18 and C20 will stuck in the column. Okay, they will not eluted. So after you apply the temperature programming, then you only can analyze. So what happened when you doing the 120? So the first one, okay, if you look over here again, the first one, they will not be separated. So we have the problem with the separation. So when we use the temperature programming, the earlier one we can separate very well. Okay, and also we can also eluted the one that is a higher range of the boiling point. That is the intention of the temperature program. If your analytes is a lot, wide range of temperature, boiling range, then you need to use the temperature program. Okay. Okay, the last one we will look into the detector. Okay, detector is important element which is used to detect the analytes or to read the analytes. So basically, uh, detector is very important. Without the detector, we cannot detect our analyte. Okay, so every components discussed in the GC is very important. Without those components, we are not able to separate, or we cannot perform the analysis. So the last components is the GC detector. So we have a lot of detector for GC. Okay, in fact, it's actually much more versatile of the GC compared to the HPLC in terms of detector. Okay, in HPLC normally we only have the MS, we only have the DAD, we only have the UV, and also what we call fluorescence. But in GC, okay, in GC we have the TCD, MS, FID, ECD, PID, NPD, FPD. Okay, so a lot of detector. So the detector of the GC we can divide it into three types of detector: a non-selective, a selective, and the specific detector. A non-selective we can also call as the universal. It means that it actually can respond to all analytes. It can respond to almost all analytes. Not I say that all, but it can respond to almost all analytes. To almost all. Okay, it means that whatever kind of the compound, the charge or the structure or the functional group, it can almost uh, be detected by uh, MS or TCD detector. Okay, then we have the selective detector. Okay, selective detector can respond to the range of compounds. Okay, for example, the FID is useful for uh, hydrocarbons. Okay, the ECD is good for the halogenated compounds. Okay, PID is the compound that containing phosphorus. Okay, a specific detector responds to limited chemical compounds. It's made very specific. For example, NPD and FPD. NPE is nitrogen phosphorus detector. It means that it can only detect the compound that contain N, nitrogen and phosphorus. For FPD, it can only detect the compound that can uh, that have the I'm not sure about F, but P is for phosphorus. Later on we will check about that. Okay, if you look over here, the flame ionization detector, KFID, is under selective detector. So a lot of question can ask you in the detector. So for example, please describe three types of detector. Okay, there's an example. For example, you would like to study the range of compounds, so of halogen, what kind of detector you need to use. Okay, so you need to be able to understand which kind of detector is useful. Okay, then you have the thermal conductivity detector. TCD is universal. Okay, so it's already mentioned over here. ECD is the selective. Okay, so halogenated compound, nitrates, nitrile, peroxide, anhydride, and organometallic. Usually electron ECD also used to detect the what we call pesticides, poisons, okay, and toxicants. ECD. Okay, so one of the common instrument is ECD, FID, and MS. Especially we should have the other one, MS. Okay, maybe later on I will describe about that, but not that much. Okay, Then we have the specific. Here is the specific detector, the nitrogen phosphorus detector, and then we have the flame photometric. Okay, I'm sorry because previously I said that P stand for phosphorus, my mistake. Okay, it's flame photometric detector. So again, but based on my, like I mentioned before, so it's very specific to few types of chemicals. For example, sulfur, phosphorus, that contains specific type of the functional group. For example, sulfur, phosphorus, tin, boron, arsenic, germanium, selenium, and chromium. It's not that FPD is used to detect this element, but FPD, FPD is the compound, okay, the compound that contain, for example, AS, the compound that contain sulfur, the compound that contain phosphorus. Okay. Then the last one we have the PID. Okay. PID is the selective detector, so it can detect a range of compound. Okay, for example here, aliphatic, aromatic, ketone, ester, aldehyde, amines, heterocyclic organosulfurs, and some organometallics. So for example, okay, please state, we give you the question, please state the best three best detectors for analysis of compound containing phosphorus. So you need to be able to detect. For example, you said NPD, FPD, and also MS, for example. Okay, that is the kind of question, the kind of understanding that you might have in case in the future you want to use the instrument. So basically, here the other thing that you can read, I don't think that I should ask during the examination because it's not actually what we call in your syllabus. Okay, for the detectors, the mechanism of detectors I will not discuss into detail. Okay, the gas chromatography, here is the advantages and disadvantages. Strong separation power, high sensitivity. Okay, strong separation power, it means can provide better separation of multiple analytes. Okay, even it's much better compared to the HPLC. Later on, we will learn about the HPLC. And also, gas chromatography can provide high sensitivity. Okay, in the HPLC, usually we measure or we quantitate at the ppm level. At most, maybe ppb. But seldomly, I never heard of the HPLC up to the PPT except for UHPLC. Okay, but in the GC, sometimes it's normal actually to test at the range of PPB until PPT. It's normal one. Okay, the normal one for the HPLC is ppm. Later on, we will learn about that. Okay, the disadvantages of the gas chromatography. Okay, this one you need to understand and learn. Not I don't like to make you guys memorize, but you need to understand. Okay, we have GC and HPLC. Okay, later on you will learn about the HPLC. The problem with the HPLC that the analytes must be volatile because we use gas, right, as the mobile phase carrier. If the analytes is not be able to volatilize, okay, not be able to be volatilized, the problem is that the analytes cannot be what we call bring from the injector to the detector. The analyte will be stuck in the column. So normally the column range is from the max temperature of the column usually at 350 degrees Celsius. So usually gas chromatography is suitable for analytes less than 350 degrees Celsius. So the analyte if not be able to be volatilized, so we need to submit for the HPLC. Then the analyte must be thermally stable. Okay, so need to understand this very well because okay, later on I will describe how actually the question can be given to you guys. Okay, but first let's I describe one by one. So the second one, the analyte must be still not described, right? So I described the first one, the analyte must be volatile. The second one, the analyte must be thermally stable. For example, okay, you have this compound, okay, compound A. When it reach the detector, so you inject, okay, inject, reach the column, and then it reach the detector, it should be supposedly to be an A as well. The compound A should not change its properties. Okay, should not change its structure. Okay, if possible. Okay, the analyte must be thermally stable. We don't want that analytes, for example, we have A but suddenly it's broken into B, C, D, or few others compound. We don't want that to happen. Okay, if the analyte is not thermally stable, the problem is that we cannot identify the parent compound. Okay, that's why. Okay, what is the example before that? What is the example, the compound that is not actually stable? Okay, one of the example is explosive. Explosive is not thermally stable, so when we apply heat, it will be exploded. Okay, that is the problem with the explosive. Same goes to the GC. What happened is, for example, I have this compound. I don't really remember exactly the structure. I think we have the NO something over here, if I'm not mistaken. Okay, the problem is when we analyze as here. Okay, but we inject the compound, we inject the standard, but a detector it's not detecting this one. What happened, this what we call this branch of the what we call compound is broken, so it left only like this only. Okay, only like this only left. So the problem is this. Okay, when the compound is not thermally stable, it will broken down into few parts, so we cannot exactly analyze by using GC. Okay, so if we it's not preferable actually to analyze using GC. You can still analyze. Okay, you know that. Okay, you inject this, it will appear this, but it's not stable. When it's not stable, is you deal with the reproducibility and repeatability. Okay. Okay, I hope you guys find about reproducibility and repeatability. I will try to ask in the class later on what you understand by reproducibility and repeatability. Okay. So the problem is with the reproducibility and repeatability. Okay. Then the sample prep must be great. If our sample prep is not great, the problem is will damage the column, and then of course it's quite expensive to change the column. It's about 3,000 to 5,000. Okay. Then of course the GC is much more expensive compared to HPLC. HPLC DAD you can get about around 200 to 300,000. But for the GC, it can reach up to 1 million ringgits. So it's quite expensive actually for gas chromatography. So gas chromatography, a lot of the application, not only in the forensics. So drug of abuse, we can analyze toxic compound, we can analyze the pollutants. Okay, a lot of things we can analyze using GC. Okay, so here's just the example. Alright, okay, next one, I will try to look back at the notes provided by the previous instructor. So basically, it just cover the types of detector. Okay, so I will not go into the specific mechanism of the detector. That is on the master level actually. Okay. Okay, let's look into the troubleshooting in GC. Okay, so you can have a link over here. You can look. I have not yet look at the YouTube video, but I will talk based on my experience. Okay, here is the normal what we call the normal chromatogram or a good chromatogram. Okay, so when we suddenly run at the next time, in case maybe 2 months later we come and then we perform the analysis, and then we see this problem, the peak broadening. So maybe we are not maintaining our column very well. Okay, that's one of the problem. Okay, usually occur. Okay, maybe we wrongly set up our temperature programming. But usually if this appear, it means that something wrong with the column. It means maybe the column is contaminated. Okay, so that the analytes cannot flow very well until it reach the detector. So that is one of the normal problem. And then we have the problem with the split peak. Okay, split peak. Okay, usually problem. Okay, like here. Okay, so this split peaks usually occur because of few things. Maybe the column is not already good. Okay, the solvent. Okay, maybe it appears for solvent. Okay, compatibility also can. Okay, the interaction of analyte. Okay, is not optimum between the active side of the stationary phase and also the mobile phase. Okay, as we know that we have the SP stationary phase and the mobile phase area. So when analytes, okay, it's not really what we call the equilibrium process. Okay, the equilibrium process where the analyte is actually diffused here and infused back to the what we call the mobile phase is not optimum. Okay, this is when actually the split peaks can also occur. Okay, if you look over here, okay, here is we call as the peak shoulder. Okay, usually I solve this issue by changing my mobile phase. Okay, make my mobile phase is much more stronger, so it can what we call push the analytes throughout the column, or absorb the analyte from the stationary phase much better. Okay, so the other issue is no peak issue. No peak issues usually it comes with the problem of the detector. Maybe the preparation is not good. Okay, you wrongly prepare, or maybe your sample is degraded also can. So no peak maybe detector. Usually I try to inject my standard, but if my standard is not appear, so I will try to prepare a new standard, try to inject again. If it's still not detected, it means that the detector is problem, or maybe your sample is degraded. Okay, that's why I said before this. Okay, I try to inject the new standard if my previous standard is not appear, okay, as in the chromatogram. So I afraid that my standard is degraded, so I try to prepare a new one. If after you prepare a new one still not detected, it mean it can probably by the detector. Okay, so here's some of the peak issue. Okay, here is the normal one, here is the bad one. The bad one we don't really want. Okay, okay, for the tailing. Okay, for the tailing, okay, the problem usually caused by a few things. Okay, first of all, maybe the compatibility. Okay, compatibility of the solvent. Okay, maybe the analyte strongly attached. Okay, strongly attracted to the what we call the stationary phase. Okay, so you need to use the compatible what we call mobile phase. Okay, you need to, or maybe you need to change the column. Maybe the column react to strong with the analyte, so column compatibility also can. Peak fronting is I think based on my experience, peak fronting, the only thing that can cause from peak fronting is the overload, column overload. Okay, maybe instead of you inject at 3 microlit, you inject 1 microlit. Okay, that is for GC. For HPLC, usually we inject from 20 at 20 microlit. If this appear in HPLC, then I will inject 10 microlit. Usually when I inject 10 microlit, it should be soft. Okay, the peak tailing is the same with the peak splitting and also peak shouldering. Okay, so the column compatibility, the mobile phase compatibility, and also the other things like such as the dead volume, also dead volume. Okay, maybe the connector or tubing is not that perfect. Okay, so here we have a lot of issues, a lot of factors can contribute to peak tailing. For peak fronting, usually the volume of injection. Okay. Okay, I will discuss about this later on during the class later on. During the class, the tutorial session later on. Okay. So I will upload in the YouTube. I will attach the link in the e-learning for the GC video lecture. I will also update my GC slide, so you guys can refer to the new slide later on. Thank you so much.